Here is an explanation for the answer to final exam, question number 88 in Electronics Demystified, 2nd edition. If you have the printed book, please see page 437. The question is at the top of that page and the illustration for it. Figure exam-15 is at the bottom of the page, and I have reproduced that illustration here. We're talking about a folded dipole antenna at its fundamental frequency. And we're being asked, what is this length L in terms of electrical wavelengths? Well, the first thing that we should do is to figure out exactly what a folded dipole is, how it's made. If we take an ordinary dipole antenna, say we have a feed line, parallel wire, coaxial, whatever, and we run a quarter of a wavelength wire off one side of the feed line and a quarter of a wavelength wire off the other side and line them up so they're all in a straight line, we get a half wavelength long antenna. That is a typical ordinary open dipole antenna. And under ideal conditions in free space, we will get a purely resistive impedance at the feed point of roughly 73 ohms. That's assuming no objects near the antenna, particularly near the ends, that would alter the characteristics of the electromagnetic field in the vicinity of the antenna. If this thing is just out in interplanetary space, if the wire is perfectly straight, infinitely thin, then in theory we get a radiation resistance of 73 ohms, and if it's a resonant, exactly half wavelength long antenna, we will get purely resistive 73 ohm impedance. Well, suppose now that we take and we run a wire parallel to the half wave electrical wavelength wire right alongside the ordinary dipole and then short out the ends. What we get is a folded dipole antenna, and the length L of that antenna is 0.5 electrical wavelength, just like an ordinary open dipole antenna. So the correct choice for this question is choice C, 0.5 electrical wavelength. We have to keep in mind that this is an electrical wavelength, and that's going to be somewhat shorter than a physical free space wavelength. Remember that a free space wavelength depends upon the frequency of an electromagnetic wave. The speed of an electromagnetic wave in free space is 300 million meters per second, or 300,000 kilometers per second. So if we use the formula to determine free space wavelength, we're going to come out with a little bit of an error in the length of the antenna itself, because the antenna should be an electrical wavelength long, and a good rule of thumb for ordinary wires is that the electrical wavelength is about 95%, or 0.95 times the free space wavelength. This 0.95 or 95% is also known as the velocity factor of the radiating element in an antenna. And for ordinary wire, a dipole antenna that you might make at a shortwave radio frequencies, that velocity factor is around 95%. If you build a folded dipole out of transmission line, the velocity factor of that transmission line might be considerably less than 95%. However, it's not acting like a transmission line when you make a folded dipole out of it. It's the characteristics are different. It's more like an ordinary length of wire, so the velocity factor will be about 0.95 regardless of the type of transmission line that you use to build this thing. You can use TV ribbon, you can use open wire line, and it'll still be around 95%. It might vary, it might be a little bit less than that just because you're dealing with a slightly larger surface area or cross-sectional area of wire here, but not much different. So the electrical wavelength should be 1/2 of an electrical wavelength from end to end at the fundamental frequency is the correct length for a folded dipole antenna. And that is choice C.